Good morning, everyone. I'm Juliana Smith and I work for Bureau Veritas. And I think this morning I would like to thank you all for making the time to join us today. I would like to thank and acknowledge the Warrawong people of the Kulin Nation on the lands in which we are meeting today. I would also like to pay my respects to elders emerging, past, present, and also celebrate the diversity of the Aboriginal people and their ongoing cultures and connections in the lands that we live in Australia. I would also like to acknowledge any Aboriginal people and Torres Strait Islanders who are joining us today. Before we get started, I would also like to acknowledge today we are going to be talking about energy yield assessments, which is a very exciting topic. I think when I talk about, the importance of accelerating the energy transition, what it means to us here in Australia, I recently lived through my first cyclone here, and I think, in Australia, we certainly have seen more frequent, more extreme weather events, and they are intensifying. So it's really important that we are moving faster as we transition through that. And I think one of the key things when I talk to people in the Australian market is the challenge to get their project bankable. And that's a really important thing. Obviously, we're asking people to invest a lot of money, and to make that decision, they rely on a lot of detailed project information, and they also need to make sure, that information is credible, it's trustworthy, and obviously success of not just one project, but the ongoing success of those projects through, getting bankability, getting finance, getting it executed, getting it operated and delivering on those expectations. That builds trust and means the capital for the next project continues to flow. So I think bankability is a really important topic when we talk about how do we accelerate the energy transition. You can obviously see on the slide there's a little bit of housekeeping. We've got a couple of hundred people who are joining us today, so that's exciting. We've also got some excellent speakers, and they are real specialists within the energy yield assessment. So in terms of format, the way we're going to run the session, the speakers will present for the majority of the time, and then we'll enable some Q&A at the end. If you have any questions as we're going through the presentation today, simply put them in the chat. And again, if you have any technical issues, also just put that in the chat and one of the team will try and help you. If I talk a little bit about Bureau Veritas and who we are, some of you will know that we're a global leading testing, inspection and certification company. We have 88,000 employees globally, and we're in 140 different countries. So here in Australia, we've got approximately 3,200 employees. And I think when I talk to people about what are the solutions and what are the services that we offer, we're a real technical organisation. We have some of the brightest and best engineers and scientists who are helping our customers manage their health and safety, their quality, their environmental and their sustainability risks. And we do that by providing a range of different services across the asset life cycle. So obviously we're talking about the clean energy sector today, and one of the unique things about Bureau Veritas is our delivery model. What you're seeing here is our technical centre or technical hubs and centres of expertise, and these hubs are really critical in terms of delivery of some of the transactional or the advisory and technical advisory services associated with renewable projects. And the beauty of this model is we've got engineers who understand the local market, the local regulations, which is really critical in getting projects done, but we're able to bring experience and knowledge and learnings and innovation from other countries to transcend borders, bring that innovation to the market much faster by replicating it. So I think that's a really unique approach, and we've been very successful in that delivery model for a number of different decades. The other exciting part of our delivery is in 2024 in September, we acquired Arcvera Renewables, and they are definitely a very important contributor to the group already. So they've only been with us for a short time, but they're already having a significant impact. I think what's really special about the Arcvera Renewable team is, they're a really niche organisation, real true specialists with credibility and experience within the renewable energy sector. I'm not talking about a couple of years or a decade, I'm talking about 40 plus years of experience, which I think is really exciting to be able to leverage that expertise and bring it here to the local market. And literally, we have already done that. So within a week of inking that deal and that acquisition, it's been great to have the Arcvera team partner with our local engineers here in the Technical Centre. We're already delivering projects in the Northern Territory and the East Coast of Australia. And customers are giving really positive feedback about that. And so it's really great that we've got these speakers able to join us here today. So I will just quickly introduce our speakers. So we've got Ralph and Cynthia, who are joining us from Arcvera Renewables. Rolf has a great amount of experience within the industry. So he's been working within the renewable energy sector across both wind and solar for the past 30 years. He's a real specialist in energy yield assessment, so it's really exciting to be able to learn from him today. We've also got Cynthia. So Cynthia's going to be focusing on the solar part of the presentation today. She's one of our brightest talents. And I think what's really great about Rolf and Cynthia is not only are they specialists in yield analysis, but they've also got experience in, delivery of services and solutions at different stages of the asset lifecycle. And I think it's really important to have that practical understanding and experience to be able to provide better insights when it comes to the energy yield assessments. So thank you very much. I hope you find the session valuable today. And Rolf, I'll hand it across to you.
All right, thanks, Jules. We're very happy to be here presenting about bankable energy yield assessments with our Veritas colleagues. So thanks for that warm welcome. I wanted to start with this slide that really kind of lays out the project life cycle. Obviously, financing is in the middle, and that's what we're going to be focusing on, that and to the left. So that's starting the early activities and trying to enumerate some of the things that we can do to proactively add value to the project. I will be speaking primarily from an owner's engineer perspective, but the topics I'm going to touch on, doesn't matter what side of the fence, if you're in lender's technical advisory, owner's engineer, pretty much the same subject matter, but just in the terms I'm talking about will be from an owner's engineer perspective. I'm going to follow a wind resource assessment outline in general, but it's not going to be a point by point. It's really going to be focused on points of pain, lessons learned, etc. So it's not going to be every single step of a resource assessment. So next slide. So bankability, what do we mean when we talk about bankability? It can be a little bit of a moving target depending on who your financing party is, but in general, investors are seeking high quality projects that minimize risk. That's kind of what it boils down to. So we need to recognize that bankability starts at project initiation. That's one ironclad rule of project development. You're not going to get that time back, so you need to spend it wisely. And doing so means that you've got plans in place, but you're also going to be flexible. So we're going to add value by enhancing the project in terms of credibility, transparency, diligence, reproducibility. I could go on and on with a list of adjectives, but those are some of the things that are going to be common themes as we focus on the technical topics. We also want to take a long-term view of the project. If your business model is such that you may be exiting the project at finance time, that sounds great, but you still want to take that long-term view. What is the project in terms of operating characteristics and things like that? You want to build a high-performing project from the very start. And so for the lifetime of the project. And so we're talking, 20, 30 plus years. And so that long-term view is pretty key. You want to apply standards and guidelines. You want to use them to your benefit. They encapsulate a lot of hard-fought knowledge, and you can really take advantage of those for adding value to your project. But you also don't necessarily want to bind yourself to a standard or guideline that's not going to provide benefit to the project. So again, that can be part of the dialogue with your financing party. And really, you don't want to just blindly follow them. You want to use them with a bit of care and skepticism. Last point, your work is going to be reviewed by a third party. If you're working on the owner side, it's going to go through lender's technical advisory review, independent engineer review. So it's good to plan ahead that you're going to have to justify your analysis, produce supporting data. So some of those types of things, if you're aware that that's going to happen, the better you can plan for it ahead of time. Next slide. So how do we do that? We start by gathering data from the project. I've got a picture of a METMAST and a couple of LiDAR units. I'm going to be speaking about remote sensing devices in general in the presentation, but it could be that I slip and focus on the LiDAR, which has become slightly more prevalent in the industry recently. So executing on the fundamentals, have a plan, work the plan. I know it's a cliche, but it's a cliche for a reason. It's really important. So we're going to want to measure for at least 1 year to capture the seasonality of the project. That is still the standard for project finance. And we really want to provide a solid basis for long-term correlation, going through measure, correlate, predict, or MCP, and going through your data quality checking. So again, 1 year is kind of a minimum. It's really hard to cheat that. People want to really accelerate project development, but having that 1 year's worth of data as a minimum is really important. Combining METMASTs and remote sensing devices to leverage their respective strengths is really important. The remote sensing devices are a relatively recent entrant to the industry, but they really do provide a lot of good information to hub height and beyond. Whereas the METMAST with the cup anemometers, hopefully, wind tunnel calibrated, so you've got calibration certificates that are traceable. And so again, they're kind of the tried and true, been around for decades, but really they kind of answer different questions from a meteorological perspective. And so combining them and leveraging both of them together is really important. Last bullet point, I hate if this sounds pedantic, but taking your maintenance and document management seriously. A broken sensor is not providing any value to the project, so make sure you're doing your corrective maintenance in a timely fashion. Document management, nothing's worse than doing a review and having to adjust the uncertainty upwards because of missing documents. It sounds like you'd be surprised how often this recurs. So those are something that it's easy to do and just something to not completely overlook and focus as you go through. Next slide. So we want to collect representative measurements. I've got multiple METMASTs on the image on the left, and those measurement locations are planned in advance to be reflective of prospective turbine locations. So we don't want to have too great of a distance between the measurement and where the turbine's going to go. We want similar elevation and exposure to the prevailing wind directions. So That's just, something that you need to keep in mind as you're laying out your measurement campaign. I've got a snippet from the MESNET guidance that, in terms of distance, 5 to 10 kilometers for simple terrain and uniform surface vegetation is sufficient. If the terrain gets complex, that reduces down to 2 kilometers. So that's the smallest of those circles on the left. And that's, so we just need to have those measurements be reflective of the turbine conditions. The second to last bullet, 50 to 100 megawatts, that's just a really rough guide. It really depends on the geometry of your landform and how the exposure to the prevailing winds that's going to set that ratio, but it'll get you in the neighborhood. Also, we can kind of bend the rules a little bit with a high quality wind flow model that correlates well to your on-site measurement. So that can be a key part of that horizontal extrapolation. Next slide. Okay, here we're talking about vertical extrapolation. So we're extrapolating up to a hub height wind speed. We can do that comparing MetMast and remote sensing data. Any comparison between the two, it's imperative that you have fully concurrent measurements. So you don't want to introduce bias to either of the data sources. On the left, we have the MetMast data in blue, the LiDAR data in red. And then I've got a little green line that just, kind of represents that if you take the top sets of sensors from the MetMast and the wind shear exponent from those, you can see that the profile of the LiDAR, as it climbs in distance, it decreases or relaxes a little bit. So what you don't want to do is introduce a high bias into your hub height wind speed when you extrapolate that. So that's one of the things we can look at the magnitude of difference between the MetMast and the LiDAR. We can look at the difference in the wind shear exponent itself, and we can make adjustments to generally the mass data to do that hub height extrapolation. Next slide. This is a brief slide to talk about buildable area analysis and wind turbine placement. Buildable area analysis typically is not part of the core wind resource, but it's a critical piece because if you don't have a solid foundation with your buildable area, you're not going to know where to place your turbines. So in a nutshell, that's gathering all of your land parcels together, gathering your constraints, setbacks, and restrictions, often set by permitting authorities or other governmental bodies, from federal to local. So you take all that, you add a little bit of GIS magic to buffer those constraint features and then remove them from the available land. And what you're left with is the buildable area for turbine placement. Again, that may be done within a development group or a GIS group, but it's something that you're going to need in order to place those turbines. So when you get to that point, generally, you're going to want to place the turbines to maximize energy production, minimize wake impacts. Optimization tools do exist out in the industry. We do recommend that you use them. They can be very helpful. You can also do that process fully manually. Some of the optimization tools are sophisticated enough to take into account linear cost for things like your electrical collection system or your wind farm access roads. So that allows you to actually optimize on cost and not just energy. So that can be a helpful feature. We really recommend that you use tracking sheets for your buildable area analysis. You should have everything listed out and tracked in terms of your constraints, setbacks, and restrictions, very similar to your layout. You're probably going to go through several iterations of your wind turbine layout. You could be considering multiple turbine models, multiple turbine hub heights, et cetera, et cetera. And having a single list where that stuff is tracked can be very important. Next slide. Okay, talking about wind flow modeling, we've got three main categories of wind flow models. At the top, we've got the linear models, such as WASP, which have been around for quite some time. They extrapolate out from the measurement locations by calculating speed up factors. It's run to steady state, so you get a single snapshot of what the atmosphere is like. The atmospheric physics encoded in the linear models is relatively simplistic, but the good part of that is that a run typically takes a few minutes, several minutes to a few hours on pretty much any PC these days. I mean, you can even run it on a laptop without much trouble. The second category is computational fluid dynamics, or CFD. In wind energy, that means you're going to use Reynolds average Navier-Stokes simplifying assumption on your turbulence closure. Again, this is a steady state solution. You're going to pick one wind direction sector and one atmospheric stability class for each run. That run runs to completion, to convergence, and then you go on to the next direction sector. By the time you run all the way around the windrows, you get that set of results, and you can knit that back together to give a fairly precise depiction of the state of the atmosphere, but it's only for a single snapshot. Typically, that snapshot is going to reflect long-term annual averages, but it's still just a single picture. Mesoscale models are numerical weather prediction tools, such as the Weather Research and Forecasting, or WRF model, which is what we use internally. Our full physics model, so it's solving the full set of Navier-Stokes flow equations, including things like microphysics packages. And it's doing so on a time step by time step basis. So you're getting state of the atmosphere for each time step. The downside of that is that the runs typically take a few days to a week on a supercomputer cluster. Internally, we've got the logistics on that pretty much figured out, so we can still do the mesoscale model and deliver an analysis report within a few weeks. Next slide. A little bit more on mesoscale wind flow modeling. That time varying atmospheric stability is really important, because that's what determines whether an air mass, as it encounters the landform at your project, whether it's going to be able to go over that landform or whether it's going to be blocked and have to go around it. So you can think of that in terms of buoyancy. Intuitively, it sort of makes sense. And so having that state of the atmosphere on a time step by time step basis, it's a much more accurate reflection of what's actually happening in the real world. And it avoids some of the severe simplifying assumptions of linear and CFD models being run exclusively to steady state. That's going to help you do your wind farm design, as we talked about a couple slides ago, optimize your wind turbine array for maximum energy production, minimize your wake losses, etc. We internally at ArcVera, we run the WRF model at a native grid resolution. So that's the full physics down to a 200-meter horizontal grid resolution. In cases of very complex topography, we can run what's known as large eddy simulation, or LES, down to 100 meters. And then those are so that's a full physics down to those grid resolutions. And then we downscale that to the grid resolution of the available topography using a mass consistent model. So it's full physics down to about 200 and then down to 30 with the mass consistent. So mesoscale modeling is our standard for finance grade assessments. Next slide. Talking a little bit about wakes and blockage, we prefer internally to talk about wind farm atmosphere interaction, or WFAI. You can see on the picture on the bottom left there, that's the well-known Horns Rev photo. It's got, we've taken the liberty of annotating some of the features. You can see that in front of that leading edge of, or the leading row of turbines, you've got some blockage. That's an area of fog. But you've also got some counterintuitive behavior going along, acceleration zones where you might not expect them. So those are things that the models can tell us that are really important. And we can run these models. We can do what if analyses, look at things like turbine to turbine spacing, site specific meteorological conditions, etc. So internally, current state, we run a suite of engineering wake models in an ensemble fashion. So we run several, including those encoded in commercial off-the-shelf software. Then we weight those ensemble members depending on how they fit site characteristics, and even we compare them to each other. So that's our current approach for doing wake modeling. Next slide. For research and development, we skipped one. Yeah, there we go. For research and development, we run the WRF WFP. The WFP part stands for wind farm parameterization. So what this is it introduces an actuator disk with a momentum sink in the numerical flow field while the WRF model is running. Again, back to the time step by time step solution of the state of the atmosphere, including atmospheric stability. Having those wakes in there is quite important. Unfortunately, it's a little bit heavy in terms of the computation. It does require the mesoscale model to be run. But the results are, the validations, whether it's onshore or offshore, are great. And so it's well worth the extra compute time, but you don't necessarily want to run it with every project. We are tracking these results carefully. Again, this is ongoing active research. We're trying to use those lessons learned and tune the engineering wake models. And one of the reasons for doing that is as blade lengths and hub heights are increasing, the engineering models, the turbines are just intersecting a different part of the atmosphere from when the engineering wake models were created. So using some of these more robust tools is important. Next slide. Talking a little bit about losses and uncertainties, at ArcVera, we had the luxury of having an engineering group that focuses on post-construction analyses, so things like operational backcast energy assessments, root cause analyses, power performance tests. And that really benefits us on the EYA side of being able to support each line on the losses table with actual project work. So when we look at things like availability, degradation, turbine performance, we've got backup by way of having done that analysis in our engineering group. So that works out great. On the right-hand side, we've got uncertainty. I've got 1 year and 10-year P levels shown. We also run 20 and 30-year standard as part of our analyses. And again, those the robust uncertainty framework is based on that experience base that from our engineering group going back decades. Next slide. So time of day summaries, we've got all these results. We can cook these down into, on the left, we have what we call an 8760. There are 8,760 hours in a year. So we've got a per hour estimate for net capacity factor and net energy production for each hour. So that can be, and on the right, we have what we call a 12 by 24. It's a month-hour matrix through some conditional formatting to show the patterns a little bit better. These are really helpful for doing things like load matching, curtailment analyses, etc. They're also extremely helpful for doing hybrid analysis, which is where I hand it off to Cynthia. So I look forward to your questions after we're all done, and take it away.
Thank you, Rolf. Thank you for all your knowledge. Yeah, so let's talk about the solar side. Well, I wanted to start by going over the flux of a bankable solar yield assessment, before establishing what is necessary for it. So first we start with a measurement campaign where you measure your local resource, in this case, irradiance being the most important. And once that is done, we can use a trustable long-term data set to correlate and predict, or establish a corrected typical meteorological year, which is going to be the base of your energy forecast. In parallel to that, you have your engineering, so you conduct your site assessment and your engineering project, and from that information, we are parties to analyze it and establish, PV system plant losses, and then model the PV plant by using the corrected data set that we establish, and two, the PV plant configuration and all the estimated losses and parameters that we assume and that we calculate. And that leads us to an energy forecast, to what is a bankable solar yield assessment and how to attain one. Next slide, please. So our goal is to accurately predict our resource, and that is going to give us a baseline energy, and accurately predict our losses, and so we can reduce uncertainties in our prediction. So how do we do that? I'm going to list some main topics that are important for that, and later on I'm going to talk individually on these topics. So first, you want to conduct a thorough measurement campaign, as was mentioned, and use it with a high quality long-term resource data for forecast. And then you want to conduct a detailed site assessment, look for any obstructions, high trees, potential shading, have a real thorough analysis of your terrain constraints. And lastly, you want to optimize your system design by selecting the most fitted O&M for each equipment, designing the layout around, and conscious of the obstructions that you find, and designing your capacity to better fit the revenue that you're striving for, right? So, okay, but why do we want to do all that? Why would we want to reduce uncertainties? Well, because accurate yield measurement, accurate yield assessments, they're crucial for an overall reliable financial model, and that is going to help secure financing and build confidence among your investors and lenders, and avoid any troubles, and really also just ensure that the system that is designed and sized appropriately to maximize energy generation and your financial return. So that is why we want to do that. So next slide, please. Okay, so now I'm going to go over a bit more detailing what those topics to assure bankability in a solar assessment are. And the first one is solar resource. You want to run a measurement campaign at least 12 months to capture your local behavior data. And usually you measure GHI, which is global horizontal irradiance, and RHI, reflected irradiance for albedo, wind speed, temperature, and it's also recommended, to measure soiling, rain patterns, and DHI is also measured in a lot of campaigns, although DHI is less common. So what are the standards and best practices for your measurement campaign? And again, as Rolf said, you don't need to go so locked in to all these standards. You can adapt it, of course, to your local campaign. So there's first I wanted to cite a few just to give some guidelines. There's IEC 61724, which is it talks about photovoltaic system performance monitoring, and there's the WMO guidelines from the World Meteorological Organization. And NREL has a guide on the handbook, I think calls Best Practices Handbook of the collection and use of solar resource, which is very much based on these two prior standards, but like an amalgam. But it has very good complementary information, and it has a comprehensible format. But anyway, what are they going to tell you? What are the parameters that these standards are going to tell you? They're going to advise you on location, which is you want to measure less than 10 kilometers of your site. The closer is the better. And you just want to portray the real irradiance at the site. So the closest you are and the closest the measurement location is similarly to the site is the best. And then it's gonna talk about the quality of your instruments, whether you have a Class A or secondary standard pyranometer, which is the same. And they're gonna talk about redundancy measurements. So you want to have two Class A or secondary standard pyranometers. And also they're going to brush off on high measurement frequency and interval. So for solar is important to have a good interval of integration. I think it's 1 minute the standard recommends, because solar is a very it can shift very fast. And as opposed to when, I'm not a wind specialist, but as opposed to when the equipment is going to respond instantaneously to it. So it's good that you have a measurement at a high frequency. And also you need to perform proper maintenance, adequate cleaning, aligning, calibration, and maintain those records. And all these actions, they're going to help you attain a measurement campaign with high accuracy. And then lastly, I'm gonna say again, you can do your solar resource modeling by choosing a high quality long-term resource data and MCP with this data with the measured data to forecast solar resource. Yeah, next slide, please. So on independent engineering assessments in BV, we often, more than not, come across projects that already have a measurement campaign, an engineering project, its technology is already defined, and our main task is to try to accurately predict and assess model system losses, the PV plant losses, right? So I'm going to go over a few of these that are more subjective or more complex, in the sense that they are not easily calculated, and they can depend on external models and measurements, and they can evolve as technology advances and as more knowledge and research around these losses are published. So first we have what I'm classifying as module and technology inherent losses. The first one being LID, which is caused by solar cells exposure to sunlight, and it happens in the first hours or days of operation. We have a graph here that represents the loss, the top graph on the left, and it just shows how all the outputs of the solar cell behave within the first hours of degrade rapidly actually in the first hours of operation to then stabilize. And the magnitude of these losses, they're going to depend on the specific solar cell or technology or manufacturing processes. Manufacturers have now a mitigation actions to stabilize these losses. And to help with that, you should carefully choose your model technology, be aware of it, and understand the OM warranties surrounding this loss. And And then another module and technology inherent loss is mismatch, which is caused by variations in the electrical characteristics or individual solar PV cells, or the modules within an array, by difference in irradiance between modules and arrays, and because of partial shading or aging or soiling. The second image represents kind of how mismatch power loss translates into the array power. And now with bifacial, additional mismatch is to be considered, it's going to be very dependent on the structure type, your tracker type, the architecture of it, the height, the albedo for your sites, how these factors are going to influence on the irradiance that reaches that part of the module, the back side of the module. And, if you have a detailed layout with structure arrangement and your backtracking algorithm, then it's easier for us to capture more accurately that loss. And lastly, for both cases, both mismatch and LID, we can also evaluate any test results from a trustable third party and take that into consideration into modeling our yield analysis. And flash tests also can be used to describe and determine the performance of PV modules, and they can be incorporated into the assessment to help determine model mismatch. Yeah, next slide, please. So now we move on to environmental losses. First, we have soiling, which is caused by dirt, dust, and other particles, matter in the surface of solar panels. And it's influenced a lot by location, climate, weather conditions, module tilt, your rain, rain is weather condition. And how can we apply our modeling into accurately predicted? It's good to have a soiling measurement campaign during your measurement campaign, and that data can be input into modeling. And we can also assess and utilize any O&M cleaning plan that the solar farm has, and as long as it makes sense, it can be incorporated into the analysis. And the second environmental loss, as I am classifying as environmental loss, is terrain losses, which is caused by shading from the terrain, both outside of the array, like undulating terrain causing shading directly on the array, but also from the terrain under your array that has, that forms a non-ideal slope and azimuth of your trackers or fixed tilt structures, if you will. And then modeling should capture dynamic placing of these trackers according to terrain. It's recommended that at some point of the project, especially for sites with undulating terrain, if your site is really flat, then maybe it's not that important, but if your site is really undulated, then it's recommended that you use a high-resolution digital elevation model and you capture terrain features, and we can definitely incorporate that into our modeling. Next slide, please. So I'll rush a little. And then we have our system losses, which is everything outside module and environmental. And so what are the system losses that I thought of bringing here? First is subarly clipping. It happens because solar resource can rapidly change minute to minute due to its stochastic nature, and typical hourly modeling does not capture subarly inverter clipping loss that can occur due to fluctuation on this weather condition. So in factors, what is going to affect most of these loss? Your project location is going to affect, and your inverter loading ratio is also a big factor that can influence the loss range. In Akvera, we model the system with long-term sub-hourly data available to try and capture these losses and then resubmit it into our model as a percentage loss. And now we have two graphs here. The graph to the right shows loss, first when the hourly average MPP is below the clipping threshold, and secondly, when the hourly average MPP is above the clipping threshold. These are two types of clipping losses. And the table to the right is a table from a resource that was done where it was measured different inverter loading ratios and compared the hourly modeling versus 1 minute actual real data. And you can see that as you increase your inverter loading ratio, it increases the difference between modeling hourly and 1 minute. Up until it gets to a point where inverter load ratio is so big that it doesn't matter anymore. But yeah, so, and then we have, for second, we have plant availability, which is your main equipment failures and downtimes, your inverters or trackers, and your other BOS downtime, transformers, your switch gears. And how we model that, we actually model it by, we build our assumptions based in our database of operational facilities. We're lucky to have that, and we try to understand better its pattern, and that's how we build our assumptions for that loss. And lastly but not least, we have grid availability, which it can be many, we can have many types of grid availability, but I'm going to talk specifically about curtailment, which can occur due to congestion, oversupply, or other market restrictions. And how do we model it? We need to know the historical data, published reports, grid operator data. That's going to help you better assess your site. And it's also recommend, although we internally don't do it, but to run a load flow and a grid congestion study. And that can be analyzed and incorporated into the modeling, again, if it's reasonable. And lastly, but not least, hybrid with storage can be a solution for your project that is suffering with a lot of curtailment. I think that's the hook with hybrid. You can go to the next slide, please. So before going into a hybrid yield aspect, I'm going to discuss resource combination of solar and wind and how that can influence on the total yield of a hybrid park. So first, you need to know your resource limitations and their behavior, hourly, daily, seasonal. And because solar is similar all around, it's the day starts as the sun is born and it rises early in the day, it puts down at night. But wind resource pattern, it can vary depending on location. So site selection with opposite correlation with opposite wind correlation to solar on daily and seasonal basis is the key to strengthen your base load. You can see the image below. We have a site where wind and solar generates them simultaneously to the left, and to the right, you can see a site where the profiles are more complementary to each other. Wind is the blue one and solar is the orange one. That's a cliche, but you can see how the sites complement each other, right? And that's when you have anti-correlation. So when you have these both sources generating at the same time, you have a positive correlation, and when you have them generating at opposite times, then you have an anti-correlation, and that's what you want to strive for. Next slide, please. So when it comes to hybrid, whether it's solar wind and BESS, or solar BESS, a lot of variants come into consideration. Not that these variants didn't come into consideration before, but I feel that solar and wind market solo, they are somehow more established and players are more accustomed to and know the rules of engagement. But hybrid can have several types of combinations that and they depend on the market, and the line that makes your project profitable can be very different. But ultimately, in the end, the purpose of the yield assessment and maybe the optimization that you're running is the same, which is you want to deliver more energy, or rather, actually, how you want to gain the most from your facility. This is what you want to understand. So that's what we're trying to keep in mind. So I listed a few topics that are not inside of the energy yield assessment itself, but they are kind of prior to it, and they're going to help define a project's feasibility or direct it towards bankability. So first is the project purpose. You need to understand the goal of the hybrid system that you want to build. You know, do you want to supply round the clock capacity for a PPA? You know, your PPA demands that you deliver some value of power around the clock. Do you want to maximize revenue for contractual grid usage? You have a contract for your wind farm, and you pay for it. You pay for grid usage, and you want your solar to utilize it also during the day when your wind farm is not producing. Do you want to just optimize your LCOE? So those are some of the uses that can be applied. And second, you want to know your regulatory and grid integration. You need to understand the local regulation and how that can potentially influence sizing and applicability. Regulatory framework also establishes market limits, and they impact economical feasibility. So it's important to understand that. And for grid integration, wind and solar generation, I put this fact here from the International Energy Agency, that it will account for 30% of global electricity by 2030. So that's a lot. And it's a rapid growth also, and curtailment becomes a challenge. Oftentimes you can have a grid and an operator that are not flexible to the intermittency of these sources, actually most of the times, and it takes time and investment to adapt it. And that is one of the cues for the best growth that we have seen in later years. And I'll brush on BESS shortly. And then lastly, you have your economical feasibility. That is going to depend on everything that came before. You need to understand your CapEx, your OpEx, your revenues, your PPA, your incentives, and all of that. And these are the topics that are not actually yield, but they are going to position the project before moving into a yield assessment. And okay, let's move on to the next slide. So I said all that to then talk a little about BESS. So once you have your purpose and all the other factors into account, when it comes to BESS, adding BESS to your hybrid project, how your goal is to evaluate how much energy the system can store and discharge efficiently over its lifetime, right? So what are main parameters to consider? You want to consider your battery capacity and efficiency, assess usable capacity, round trip efficiency, C rate. You want to consider your degradation in lifetime, consider your cycle life and end of life capacity to estimate long-term energy yield. And you want to check your operational strategies, whether you're going for peak shaving or time of use optimization. And just to finish off, I know I'm going talking way too much. And showing showing an accurate simulation and uncertainty analysis, you should use your load and renewable solar and wind or hybrid source profiles. Make sure you understand your market pricing and grid constraints to model energy yield and assess, sensitivity to losses and degradation. And that is it for my part. I thank you. I'll give the world back to Jules.
Yes. Thank you very much to the speakers. I think there was definitely some insights there, and I'm very conscious of time, but I think some of the key aspects or key takeaways for everybody is, regardless of whether your energy yield assessment is for a wind, a solar, or a hybrid, it's really critical. Independence is key. That experience really does matter, the credibility in the data, the ability to have that iterative or flexible approach. So some of the scenario analysis or what ifs that the team were talking about, I think are all really, really important things. So thank you very much, Rolf and Cynthia, for that. We've had a huge amount of questions actually come through. So I know we are definitely not going to get an opportunity to go through all of them. I also know there's maybe one or two individuals who have asked multiple questions, so we might need to set up a separate session with those individuals. But before I get into the questions, so some of these questions have also come when people were registering. Cynthia, this first one for you is your view on degradation for solar projects. You're still on mute.
Okay, can you hear me? Well, we do take into consideration that the major component of a solar farm degradation occurs on solar modules, which are the source of energy. We also like to factor in that environmental stresses due to exposure, they are local and weather dependent, and that's why I'm not closing in on a percentage loss here and saying, oh, that's that percentage. I don't think that's very responsible. But another factor that we take into account is that other consequences are going to come from module degradation, such as increase in mismatch, and modules are not going to degrade evenly, and that will affect overall mismatch and can translate it into stress of your BOS. And lastly, like is technology dependent? What I mean is that it's going to depend on the module type, and we need to pay attention to that and be aware of new research and information about it. For example, we are aware that bifacial modules can potentially be more exposed to degradation than monofacial, so we could estimate a placeholder, but solar farms, they are installed and they're operating and operated as technology progresses. So we are living through it, and we might, of course, change that understanding as we gather, more and more data about it. I think that's my understanding of it.
Great. Thank you very much for that. Rolf, I think this one is probably for you, and it's probably the last question before I wrap up. I'm just conscious of time. So what are the implications of changing policy frameworks on energy yield assessments, and what is that impact?
Yeah, when regulatory frameworks change, it's kind of a macro forcing function on the whole process, that whole life cycle. Typically, that's going to hit the project developers first. And from a wind resource perspective, we're providing support for that development group. So things like local regulations on met mast height, if there is a cap, whether it's aviation related, crop dusting, there are a variety of reasons, visual impact. That might skew your mix of MetMast and remote sensing device towards the remote sensing devices. Going with a ground-mounted sensor is going to be fine from that particular regulation. There are also it can change your power market, the PPA terms. You might need to provide different time of day analyses to support that. Again, there's a many different ways that we can kind of slice and dice the data, and again, providing support through the development group, so that they can give them actionable information as they pivot the project to conform to the regular change in regulations.
Okay, excellent. Thanks, Rolf. I'm going to wrap it up and respect everyone's time. So thank you once again to our speakers and also to the audience members for all joining. I think you actually saw on the last screen there was a QR code. We are going to be circulating a copy of the slide pack to everybody, and we will try and follow up as best as we possibly can with all the questions that have come through. But that QR code, just for everyone's knowledge, we are currently doing a market survey. So it would be fantastic if people could take 5 minutes out of their day to answer that as well. Thank you very much, everyone, and have a great day.
Yeah, thank you, everybody.
Thank you.